Today, Lewis and I are going to talk about transformers and how you can use the Huggingface ecosystem to apply transformers to your use case. And we plan to do that like pretty hands-on. We have a rough plan of attack. First, we want to show a little bit like what transformers are and where they come from, like just a very rough like introduction to transformers. Then show a little bit like where Huggingface comes in, what Huggingface brings to the table if you want to apply transformers to your use cases. And then like in the second half of this workshop, we want to really go hands-on. So we're going to show you in code how you apply transformers to your use case. I'm going to give like a brief overview of some tasks, and Lewis then gonna do like a really hands-on training. So that's like the rough outline. As I mentioned, starting with transformers and the ecosystem, and then showing the applications that you can tackle with transformers. And after this short break, that's when Lewis is then going to show you how to train and deploy transformer models. We already talked about us. I show this slide as a reference if you're interested. We both work on the Huggingface course and the book. So if the things you see today and hear today are something that you want to further pursue, the course is a great place to start. There's like the first part is already out, so you can get started. And in November, we're going to release the second part. So that's also exciting. And then the book is at the moment in early release. So if you have access to the O'Reilly platform, the online platform, you can already read most of the chapters. And at the beginning of next year, probably is when the hard copy is out. Good. So let's have a look at like what where transformers are at the moment, like in the real world. One of like the most popular example of the past few months is probably Github Copilot, which is a collaboration between GitHub and OpenAI, where they trained a model to generate code. And they integrated that model into VS Code, for example, where you can then type a piece of code and the model will predict for you like what the next few lines of code should be. And this model works really well. You can try it out. I mean, it comes with pros and cons. It's really nice. It's really good at completing boilerplate code. Sometimes it can cost you some time because maybe it doesn't quite do what you intended it to do, and therefore requires like some debugging from your side. Another very famous example of transformers in the wild is Google search. Google famously now uses BERT, a transformer model, in most of or in a big fraction of its queries. So if you type something in Google search, there's a good chance that your query goes through a transformer model and is improved that way. And then lastly, touching on Cornelia's comment previously, a really exciting project that uses transformers as well is AlphaFault 2, which is a project from DeepMind where they use transformer models to predict the folding of proteins. If you've ever worked with proteins or chemistry, you know that protein folding is a really hard problem. It requires either really large computers to calculate how proteins will fold, or you need to do like very expensive experiments. So the ability to use transformer models to actually predict protein folding without like a supercomputer or an expensive experiment is like a really big deal. And that's exciting research coming from DeepMind. So what is a transformer? The transformer was introduced like in a landmark paper by Google, which was called Attention is All You Need. And if you look at that paper, you likely will have seen like the diagram on the left. And if you're anything like me, that's probably the face you made when you saw that diagram. It's like it looks very complex and it's a little bit hard to read. So I want to try to break it down and motivate a little bit where that diagram comes from, because it didn't just like appear out of nowhere. There was some evolution of architectures that led to the transformer. If you want to break it down, what made the transformer so successful, it's on the one hand an attention mechanism. That's the first thing I want to talk about. And then a combination of self-supervised pre-training and transfer learning, where you can use these pre-trained models and adapt them to your use case without a lot of training data. So let's first have a look at like where the attention mechanism comes from. When you do like a task like translation and you go back like a few years, this is probably the kind of architecture that you would be using. So before transformers, like the state of the art for natural language processing were recurrent neural network. And I show here like a diagram for how such a architecture would look like if you wanted to do, for example, translation. Translation is a sequence-to-sequence task. You have an input sequence, like the sentence in the original language, and you have an output sequence, which is the sentence in the target language. And for this sequence-to-sequence task, you usually use like an architecture, as you can see here, with an encoder block and a decoder block. So what the encoder block does, it takes the input sequence. So transformers are great in that case, and it passes it through that recurrent neural network. You see here that the recurrent neural network appears several times on the left-hand side, but it's always the same cell. So the RNN cell gets transformers as an input and then feeds its output to itself in the next step where it looks at R and so on. So that's one RNN cell that feeds back information to itself. After it processed the last token, in that case, like the exclamation mark, it outputs a state, and that state is then passed to the decoder block, which consists of the same RNN cells, but a separate one. So that's a new RNN cell. And the task of that RNN cell is now, given that state, expanding the state to the output sequence, the target sequence, in that case, like transformers in großartig in German. One issue with that architecture, however, is like that you have an information bottleneck. So you need to make sure that whatever that state is that the encoder outputs contains all the information that's necessary to generate like the output sequence. And especially if you go, for example, for a very long sequence or complicated sequences, then it can be like a bottleneck, because if some information is missing from that state, or it's not possible to fit all the information in that state, then the quality of the output sequence will suffer from that.
Leandro, can I ask a question?
Yes, go for it.
So what exactly is a state? What are we talking about here, kind of from a computation perspective?
Sure. So a state is essentially just a vector. So it's an array of numbers that are outputted. And that's where you maybe can also already imagine like why it could be difficult to store all the information in such a vector and then decode it to an output sequence, because you have like exact objects on the left-hand side, right? Maybe you have a date in the input sentence, and then you need to make sure that date that's in the input sequence is represented exactly in the state, so that the decoder can then reconstruct the exact date that you had originally. Does that answer your question?
Yes, perfectly.
Awesome. So people were aware of that issue, and a few years ago, some people came up with a solution that helps improve or overcome that information bottleneck in between. And the core idea is that instead of just creating one state at the end, which just represents the whole input sequence, you can create a state at every step of the way. So you can create a state after the RNN cell passed transformers. You can create a state after it processed R. And that way it can have a more granular structure in those states, which are still vectors. Then doing that's the easy part. The question is now, how can you make the decoder block in a way that it can processes all these states efficiently? What you can't do is you can't just concatenate all the states and pass them to each to the RNN cell at each step, because that state will get too big, because you have maybe thousands of input tokens. So you have thousands of states. So that doesn't work very efficiently. That's why people haven't just done that. And the second thing that was needed was the attention mechanism, which is, in a sense, a mechanism to prioritize these states at each step. So, for example, if you're here, you already decoded the first word. The model determined that the first word should be transformers. Then you get to the second step, and now the model needs to determine what's the next word after transformer. And what the model now can do is essentially it can pay attention to any of the states. And the paying attention means essentially assigning a weight to each state and thus prioritizing it. So it can say, probably transformer, that's not so important. I already know that I created or I translated that word, so I can pay less attention to the first state. Probably the state after that is pretty important, because I'm also at that step. Depending on what kind of structure of sentence you have, maybe you also want to look at other words that might influence your translation. And with that mechanisms, you can pretty efficiently then parse all the states that are generated by the encoder block and generate the translations. And that made already like a big improvement over just having the architecture I showed before.
Just one comment here. So why couldn't we just translate word for word, like just figure out what the one-to-one mapping is?
Yeah, I'm just getting to that. One issue is that there's not a one-to-one map usually between languages. Some languages are very similar. Like that example here is probably a bad one, because there's a one-to-one map between each word and its translation. But if you go, for example, to French, it could be that a word that's just one word in German is two words in French. And it gets even worse because the order of sentences can change. And that's probably something you noticed when you speak with a non-English native speaker, and all the sentences are kind of mixed up. And you always use like the wrong word order. That's not very native to English. And a good example of exactly that you can see here, where that's the attention visualized for an English to French translation. So you can see there's an English sentence: the agreement on the European Economic Area was signed in August 1992. And in the translation, you can see the effect that I just mentioned, and that's European Economic Area isn't in that order in the French sentence, right? It's the other way around. They're turned around, and you can see that model. That's the attention that you can see here of such a translation model, that it actually pays the attention the right way. So if the diagonal is highlighted, that means when looking at the word de, it looks at or when translating the word de, it looks at this word. But you can see here in the European Economic Area, it actually shifts the attention not to the one-to-one map, but to the word before or after. And similar, you can see here, was signed is actually translated into 3 words, because it is signé. And you can see that the word that the model represents that in the attention.
Maybe one thing to mention here is these pixels that you're seeing on the screen, they're just they're like numbers. It's like a heat map, basically. And yeah,
so they're just those weights I just mentioned.
Exactly. And so the when we talk about weights, what we mean is just taking these numbers that you see visualized here and then multiplying them by the various states that the encoder produced. And so that's how in this process, the decoder is able to determine, if I want to translate the word European, I should look perhaps at the other surrounding words in the original language to figure out, do I need to flip the order?
Mm-hmm. Thanks. So what made the transformer really special is to take that idea and take it one step further than just having an RNN with attention. And the idea was that if you can model much of the sequence with this attention in the decoder block, maybe you can do the same in the encoder block as well. So when you process the input, and maybe if the attention mechanism is good enough at modeling the sequence, then you actually don't need the recurrence anymore. And that's why the title of the paper was "Attention is all you need," because they got rid of the RNN in the sequence-to-sequence model. And you can see here how that looks like on the left-hand side, like the encoder. Whenever it processes one word, it can also look at all the other words to create like a meaningful state for that word. And then vice versa, similar to how we saw before in the RNN with attention case, you can then see that the decoder block can, for each token it processes, it can look at all the states that were created for all the input tokens. And that little difference of removing the RNN from the architecture and replacing everything here where an RNN was with a feed-forward network made a huge also computational difference, because if you just have feed-forward networks in your network, that's way more efficient to train than an RNN. And that's the reason why that scaling race that you maybe saw in the news recently, where OpenAI trains larger and larger models with transformers, that's because these transform models are so much more computationally efficient to scale. And we can have a look at what the attention mechanism in a transformer looks like a little bit. And here you can see an example of two sentences that have been given to a transform model. And the first sentence is "time flies like an arrow." And the second one is "fruit flies like a banana." And in both cases, you can see to which tokens the transformer pays attention to when processing that specific token. So we can see when the transformer processes flies, it can look at all the other tokens in the input sequence. And for example, it determines to create a meaningful state for the word flies, it's important to look at the word arrow, because that influences the meaning of flies. In the second case, where we have an identical word, it's also flies. But now the transformer pays attention to different words. For example, it pays attention to fruit and it pays attention to banana. And because the model can pay attention to other tokens when it processes the token itself, that kind of attention is called self-attention. So you can pay attention to your own token, but you can also pay attention to all the other tokens that are in the sequence when you process a particular token. A different way to visualize that idea you can see here, and the idea is that each of these words, it's the same two sentences that you just saw, but for each word you can now see that has kind of an embedding. And what the self-attention does is essentially it creates a weighting for each between the word and all the other words, and then it mixes the embeddings of these words. So the embeddings are just the numerical representation within the transformer, and you can see like arrow maybe has like a very particular representation that should just represent the vector, and the green should just show that it's different from the other vectors. And when flies is processed, it mixes the words that are most important to it, or that it pays most attention to. And you can see in that case, it mixes some blue because probably time is important, and arrow because fly refers to the arrow. And similarly, in the second case, you can see that banana and fruit have a very distinct color, which means they have a distinct representation. And in the self-attention mechanism, when we create like a representation for the word fly, it mixes the words that are most important for that word. So in that case, it creates something that's a little bit more orange and purple, because those are the words that it probably paid most attention to. And that vector then is very different to the vector we got for flies in the first case. So you can see, or what that should mean is that the state for flies in the first case is very different from the state in the second case. And in the first case, like that's probably similar to the verb source. And in the second case, that's a representation of an insect. And this is called like a contextual representation. So you create a representation of the word fly that depends on the surrounding words. Another concept that you might be familiar with if you work with NLP are like word embeddings or word to vec. And these are like contextless representation, because the word embedding you take for a word, they're independent for the current context. And transformers, in a sense, fix that. Are there any questions so far?
There's none in the chat right now, but maybe I have a question. So why do we care about contextualized representations?
Yeah, so if we didn't have contextualized representation, we wouldn't have a way to differentiate between those two words when we process them. Essentially, if you just look at them, they're the same word, right? Or another very popular example is if you take apple, it can be like a fruit, or it can be a tech company. And what word is meant depends on the context. So if we are able to create a state based on the context, then we're able to differentiate words that otherwise would be the same.
Nice.
Good. So when people talk about transformers, it's kind of an overloaded term. So the transformer architecture initially is what I just showed you with the encoder and the decoder block. But people also refer to BERT and GPT as a transformer. BERT is like the very famous model from Google that's really good at natural language understanding. So if you want to build like a sentiment classifier or an entity recognition model, then probably use something like BERT. And GPT, the GPT family is really good at generating text. And people found that you actually don't need the full encoder decoder architecture for these tasks. So if you just want to do natural language understanding, so you have tasks like classification, sequence classification, or even token classification, then you can use a model like BERT, and BERT only uses an encoder. And vice versa, if you only are interested in generating code, in generating text, but you actually don't really have an input sequence, so you don't want to do translation, but maybe you just want to do predictive typing, where you just want to predict like the next few words, then the GPT family is really good at that, and that only requires a decoder. Another famous example that uses both an encoder and a decoder is T5, which is a model that takes an input sequence, which can be a task description, like translate this sentence from English to French, and then encodes that with an encoder, and then creates the the solution in the decoder. And that's like more a traditional transformer architecture that uses both an encoder and a decoder. And we're going to have a look at like a few of these models a little bit later on again.
Leandro, we have a question from the audience from Amrit. So he's asking about the previous slide where he says, are these self-attention scores calculated based on a dot product or some other mechanism?
Yes. I mean, essentially they're calculated with a dot product, but it's a little bit more complicated than just a dot product between the input sequence, the input vectors. What you usually do is you create a query, value, and a key. And the idea is if you're coming from information retrieval, those are the terms that are used to look up something. So you take that vector that you're currently looking at and you encode it as a query vector. And then you encode all the other vectors as keys. And then you do the dot product between the query and all those keys. And the value is then what you actually take from these vectors. That's a little bit more complicated than what we plan to show today. But if you're interested, there's like a really great tutorial by Jay Alamar that shows visually like how you come from these vectors, you create these queries, keys, and values, and how you then create that self-attention score. I think we're a bit tight for time to explain that in detail here.
Yeah, I'll put that in the chat. But we have a follow-up question from Michael Gross. So he's asking, when using a contextualized model, the importance of a word depends on the sentence you're processing. So how do you deal with new sentences during inference? Do you need to somehow recalculate or adjust the weights, which will also need more inference time than the contextless models?
Yeah, so hi, Michael. I think we know each other. So you're right. So in the contextless case, you essentially just have a lookup, right? You store all your word embeddings in a table, and then you have a mapping between every word that you care about and which embedding that you need to take. When you do self-attention, if you have a new sentence, you have to pass it through the transformer, which is a pretty big model, and then it calculates the new contextualized embeddings. So that's definitely more expensive than the contextless models. I hope that answers your question.
And yeah, just one final related question about attention from M. Kumar. They're asking, what is multi-head attention, which is something that I think we hear about a lot when you hear about transformers.
Mm-hmm. Yeah, so multi-head attention is essentially like a duplication of what I show here. So that's like a single head of the attention. And in multi-head attention, you do that several times at each step. And at each head can take care of different aspects of your input sentence. So maybe my attention head I have here mainly looks at relations between verbs and subjects in a sentence. And I can have a second attention head that maybe models more like adjectives and other words, these type of things. So you duplicate this process. I mean, I said now, I talked about like very concrete concepts that each attention head can learn, but those are all learned by the model itself. So when you inspect these attention heads, you can see that they model different things. You don't hard code that into the model, but it's useful to have several of those. I mean, another similar concept to maybe think about why you want to have more than one attention head is if you have a convolutional neural network, usually you have many filters that you apply to the same image, and each filter takes care of a different aspect of the input image, right? You can have like maybe an input filter that looks for corners, and maybe you have an input filter that looks for edges, something like that. And it's kind of similar for these multi-headed self-attention mechanisms, that you just have the attention mechanism multiple times, and each head can model certain aspects of the sequence. Cool. should I continue?
Yep.
Awesome. So that's more from the architecture perspective, like what makes the transformer special. But there is like a second ingredient that's probably as important, if not more important than the architecture itself, and that's the modern paradigm of transfer learning. So what you do with these transformers is usually you apply some kind of pre-training to them. So you start with a randomly initialized model and you train it on a very large corpus, which is usually very expensive. And you have to do that for many days. And I mean, nowadays, even weeks or months on hundreds of GPUs. And modern models can cost anything between a few 100,000 K and millions to do that pre-training step. Depending on the model you use, that pre-training step takes different shapes. If you have a GPT-like model, what you usually do is you take a large data set, which can be a crawl from the internet, and you just try to predict the next words in that large corpus. So for example, you put the word my into the model, and you wanted to predict the next word, which could be my name. Then you pass in the first two words, the one my and name, and then you want the model to predict is. And then you can continually doing that. And the beauty about this approach is that you don't need any labels because the text itself is its label, right? It's just always predicting the next word. So the next word is the label. So you don't need any labeled data, which makes pre-training very attractive because you can train these models on large corpora without needing to employ a lot of people to label your data. A similar but slightly different approach is used for models like BERT, where instead of predicting the next word, you take the whole text and you just mask several parts of the text. And then the goal of the model is to predict what the masked word is. That's kind of like these gap texts that you maybe had to fill out in school. And you do that on these language models as well, where you predict and try to predict the mask tokens. So you do that in that pre-training step for a very long time with pretty large models, which then gives you like one of these pre-trained models. And then you can use these pre-trained models and just fine-tune them on whatever tasks you're interested in. So the advantage of just being able to fine-tune them is that you don't need that much data anymore. These models learn a lot of useful stuff about text in the pre-training phase. So you can only show them or train them on a handful of data, and you get pretty good results already. And at the same time, this also only requires like limited amounts of compute. So usually we can just train on a single GPU, and we can achieve like state-of-the-art results without having access to like massive resources with hundreds of GPUs. And that gives us like a fine-tuned language model that we then can use for our use case. There's still some challenges with transformers. I don't want to be here and claim like they're the solution to everything. They're really awesome, but they have some limitations. One limitation is that the transformer models are still very centric around English or European languages. So if you're working on a low resource language, maybe Romansh, then you might have issues with transformer models. But I mean, generally, they're like at the moment models that work for like hundreds of languages at least. Another thing is that they're still data hungry, especially if you want to pre-train a language model, and not everybody can afford to pre-train a model if they want it. Not that that's always necessary, but in certain circumstances, it would be nice if you could do that without too many resources. Another thing is that transformer models are to a large extent black boxes. although we can look at attention and we can see like at which word transformer model looks when it makes a prediction, that's not the same as actual causality. So we can see relations between maybe inputs and predictions, but we can't say for sure that that's the reason a model made a certain prediction in a certain situation. And the last thing is mainly related also to the training data that is used during pre-training. When you train these transformer models on text from the internet, they pick up all sorts of biases. So it's very easy to show that you can prompt GPT-2 to generate, for example, racist text. And that's something that you need to be aware of if you use these models for your use case, that these biases exist in the data, and you should check if they influence like the predictions that you make.
I've got a question, Leandro, on these limitations, and it's one that I've experienced personally myself. So can you comment on the limitations of transformers when it comes to dealing with long input documents? And I think here, like a really good example is like if you want to do, say, summarization, and your document is like maybe, I don't know, 100 pages long.
Yeah, that's definitely a limitation of transformers. Usually they have like a limited input window. So you can input them some text, but that text, the length of that text is limited. In most models, it's something between 1,000 and maybe 4,000 tokens, which roughly corresponds to words. So you can maybe process a page with a transform, but if it's more than a page, then you need to come up with other strategies how to deal with those documents. That's also pretty much an open question at the moment. There are certain techniques that you can apply in places, but there's no uniform solution how to tackle long sequences.
Yeah, I would just maybe comment, and I'll put the link in the chat, but OpenAI very recently published a paper showing how they were able to summarize whole books using a transformer architecture, but they had to kind of combine this with reinforcement learning and a lot of human annotators so that you could kind of decompose a book into chunks, and then you could generate summaries for these chunks, and then you could hierarchically build up from these like small summaries an overall summary of the book. And I'll put a link to this, but I think, as Leandro said, that's still, you know, far away from, you know, what we humble data scientists can have access to, because, you know, we don't have GPT-3 lying in our, you know, bedroom.
Yeah, not yet at least.
There's another question from Abhimanyu, who's asking, how immune is fine-tuning transformers to catastrophic forgetting? And are there any good strategies to avoid this when using transformers?
Yeah, so usually catastrophic forgetting is not such a big deal with transformers, because you only fine-tune them very quickly compared to like how long you pre-trained them and how strongly you pre-trained them. But it definitely can happen if you train too long. And I think fundamentally, usually you don't care too much about catastrophic forgetting, because you train your transformer for a downstream task. And if the performance on the downstream task is okay, then you maybe don't care so much about other stuff that the model has forgotten. So imagine you do sentiment classification with a transform model. Maybe you don't care so much anymore that the model memorized like all the presidents in US history. And I can imagine that information is lost during fine-tuning to some degree, but also it's probably not so important for the thing that you're trying to do, unless you want to go back after fine-tuning the model and predicting the presidents, in which case it might be bad. Another thing that maybe Lewis will talk about a little bit that shows that catastrophic forgetting is not such a big deal is that you can do cross-lingual transfer when you train a model on a one language. So what I mean by that is there are some models that are trained on several languages in parallel. For example, let's say French, German, and English. And after that, you can train a sentiment classifier only on German. And the model will then also work to some degree on the other languages, which is a very nice feature because it means you don't need to train on all the languages to the same extent. And there you can see that catastrophic forgetting is not such a big issue.
Yeah, I think this generally happens if the domains are very different. That's the few times I've seen it happen personally. But if you're in roughly the same domain, if you don't try to use BERT to predict protein sequences, you're probably okay. We have another question, which is relevant to, I think, one of your earlier slides, which is, what do I get from a pre-trained model? Is it the embeddings for each token?
You mean in that one here, essentially what what is transferred in the green part. So what you transfer is the weights of the model. So that's on the one hand, like the embeddings for each input token, but also I think if I go back here, you have these feed-forward networks that process the tokens, and they have some weights that are also stored. So when you store a pre-trained model, you save all the weights from that model, essentially. The only thing that you usually change is something at the very end of the model that's specific to your task. So if you're predicting classes, for example, sentiment, you probably have a thing at the end that has a small neural network at the end that predicts 2 classes. And that's different from the very end layer of the language model, which predicted the next token. So that thing you replace, but everything else you take over when you do transfer learning. I hope that answers that question.
Yep, I think we have no more questions right now, so we can continue.
Cool. So now that we've cleared up like what the transformers are and a little bit why they're so exciting and why you want to use them in your industry projects, it's pretty natural as a data scientist to ask, can I have this? I want to use this in my real use case and apply it to my problems. And when you go and look at these papers that release those new model architectures, for example, if you go to the Attention is All You Need paper on arXiv, nowadays, like very often, these models are like released in code as well. But that's not a very heterogeneous process. And a way to illustrate that is when BERT was released, which was very successful at many classification tasks, for example, a lot of subsequent models were released that did some tiny changes to the original architecture and changed the code in various ways. And then it can, on the one hand, be a bit confusing which one of all these models should you use on the one hand. And if you made up your mind which model you want to use, you go to the GitHub page and probably you see some issues like that. So the code is in Python 2, or it's not documented at all. They have a very idiosyncratic maybe API that doesn't make sense for the use case you want to do. So if you're lucky, you find a model that you can apply to your use case. But if you want to try out a different model, probably you need to refactor your whole code base. And that was pretty much the state until like very recently. And what we at Huggingface want to do is we want to improve that process, and we want to democratize all these models that are now available so that every data scientist can easily use them without the knowledge of like 10 code bases from research and academia. So we try to do this like in a community effort. Like we build the libraries, but we also rely a lot on community contributions. And we try to do this in an open source way so that everybody can see what the code base looks like, what we're developing, and everybody can contribute. And this has succeeded pretty well, I would say, in the past few years. And the libraries that we develop, for example, the transformers library or the datasets library, they make your life much easier if you want to apply these models to your use case. And We're going to see a little bit more about the transformers and the datasets library in Lewis' hands-on part, where he really shows you how to train a pre-trained model with the transformers library and use the datasets library, for example, to make the data processing very easy. But this is just now one part of an ecosystem that has been rapidly growing in the past few years. So probably maybe you have heard of the transformers library, which is like the central piece that we've developed. And recently the datasets library, which are used to load these transformer models to apply them to use cases and pre-process the data. Central part of the transformers library, if you've ever used it, probably the one function that you might remember is the from pretrained function, where you can just go select any model, and in the code you just say from pretrained, and it loads that model for you and downloads the model for you. And that's made possible with the hub. So the hub is now the central piece of our ecosystem, where we store all the models. At the moment, I think there are like 20,000 models on the hub roughly, and you can download all of them in the code with one line of code. But also data sets and metrics and documentation is on the hub. There are a few other pieces that are very exciting. On the one hand, we have like integration with AWS and SageMaker, so you can train models with SageMaker, and you can also serve model with SageMaker. Another thing we're offering, which is more once you have trained a model and you just want to apply it in to your use case, you can host it on Huggingface, and we do the inference for you, so you don't need to have infrastructure to run it. Very recently, we released Infinity, which is a project that takes that one step further and heavily optimizes your model for inference time. So you can achieve like millisecond inference time with huge transformer models. Another project that we're really excited about is AutoNLP. That I think Lewis will also talk about it a little bit, which helps you train models without actually needing to code. So you just specify a data set and a model, and it trains it for you and figures out what the best configuration is. And finally, a thing that I want to mention is like the spaces thing that we're also going to see today, which is about creating demos, quick demos for your models. There are two other things, Accelerate and Optimum, which are more on the side if you really want to train and optimize your model in detail. Those are the libraries that you can use, but we are not going to talk about them today. So all the things we're going to touch today are here in red. So there's like a pretty big plan ahead of us still. All the things we want to have a look at. And yes, that would be the end of the things I just wanted to show you in the slides. And I want to now go over and actually show you a few transformers in action. Are there any questions at the moment before I go over something I forgot to mention?
There's none in the chat right now, but maybe we can just wait a few seconds.
Sure.
Unless maybe if Nina, did you want to do some live questions now, or do you want to do them at the end of Leandro's demo?
I think we're going good on time like this. So if there are no questions in the chat, we can. So this is before the break, correct?
Yeah. So Leandro is now going to just show a couple of transformers in a notebook, and then we'll take a break.
Okay. Then let's have the live Q&A right before the break. Perfect. After the demo. Thank you.
Cool. So in that case, I don't think we need to wait anymore. You can just ask the questions live, like in a few minutes after I demo a few models. So to demo the models, we created a repo that also Lewis will use, and you can just go to that link. It's on Huggingface workshops, and you can go to the NLP Zurich folder, where you can find all the notebooks that we're going to show today And I'm going to give like the transformers tour. So if you go to that notebook, you should see an opening Colab batch at the beginning. And if you click on that, that should open the notebook in Colab. The one requirement, I think, for this to work is that you need to have a Google account so that you can actually execute something in Colab. But other than that, all the installation, everything is handled in the notebook itself. So what I want to do in this notebook is I want to give you just a brief taste of all the kinds of things that you can do with transformer models. And then Louis is going to go and dive deeper into one specific type of problem and show you how to actually train a model. The thing that I'm going to use, is that big enough, by the way? Should I zoom in a little bit?
Yeah, maybe zoom in a little bit if you can.
Oops, wrong way. Like that?
Yeah, I think that's good. Yep.
Cool. Awesome. Thanks. So the thing we want to show in this notebook is just the various things you can apply transformers to your use case. And what we're going to use for that is an object called the pipeline. And the pipeline essentially wraps all the necessary pre-processing, all the model inference, and the post-processing of your prediction. So the nice thing is essentially text goes in and predictions come out of a pipeline. And you can do this for many tasks. If you want to know more about the pipeline, there's a great video, which is part of the course, which I linked here. So you can just watch that video, and Sylvain is going to explain you in more detail, like how the pipeline works and what it does under the hood. Just before we can run any code, we need to make sure we installed everything. You can click run anyway if you trust us. We just need to make sure that transformers is installed and sentence piece. Sentence piece is just a helper library, a tokenization library. So that makes sure that we can tokenize the text in and go from raw strings to integers. That's what sentence piece does. That shouldn't take too long. And I have another helper function, the wrapper here, that will just make sure that the output texts are nicely wrapped when we print them. So before we start, let's look at like an example text that we might have and we want to process. And we create like a synthetic example here where it's like a complaint to Amazon from Bumblebee. Bumblebee ordered an Optimus Prime action figure from an online store in Germany, but unfortunately, like Megatron arrived and he's pretty unhappy because he doesn't like Megatron and he doesn't like the Decepticons. So he wants his model to be replaced with Optimus Prime. But you could imagine like that's a pretty normal customer feedback that you might get if you have like some online store. So let's see. Now we can see like the wrapper function in action. It's just make sure that we don't have like the text going all over the place and it's nicely wrapped at a fixed width.
Maybe just to clarify, like, because sometimes it might depend on how old you are, but like if you're old like me, the Transformers franchise was like a cartoon when I was a kid. And you had like these robots like Optimus Prime and Bumblebee who were part of the Autobots fighting against Decepticons, which were like these bad robots. And I think almost a lot of the success in machine learning models seems to be by picking a good name. And I think calling, the original model a transformer was just a great choice for, capturing the public attention and also for generating tons of memes.
Indeed. It's either Transformers or the Sesame Street for naming transformer models. So you probably heard like Bert, Ernie, and so on. Good. So we have a text, and a first natural thing to do if you get such a text is maybe you want to know what is the sentiment of that text. And sentiment classification is like a popular task with transformer models. You can see here like an example of how the pipeline roughly looks like under the hood. Like you have an input text. Maybe it's like Crystal Lance loves San Diego. That text is tokenized, which means it's like split into smaller pieces that are then fed through the model. That's essentially the thing we saw in the slides, where each of those tokens will then create a state. And that's what you can see here, like the red circles. Those are essentially the states that the model, the BERT model, then creates. And then at the very end, we can take the states. We can just pick one. Usually there's like a dedicated classification token, which has a special representation just to do classification. And we can use the state of that classification token, apply a little model on that, on top of that, like a dense layer. That's just a feed-forward network that then makes a prediction. And everything below, like the green box, that's the pre-trained model that we can reuse. So all that stuff, like that's the very large model, we can reuse that. And then for a special case, use case, we apply like that small modification on top. And we can import the pipeline from the transformers library, and then we set up the pipeline for text classification. So we need to specify the tasks that we want to do. And you'll see in a second that this will actually download something, because we haven't downloaded anything yet. See, Colab seems to be slow today. Now I think it's getting started. Good. So you can see we get a warning. No model was supplied. Defaulted to DistilBERT based on case fine-tuned SSD2 English. So what happened is we just specified a task, but we didn't say which model we want to use. And for each task that you can specify in a pipeline, there's like a default model in the background, which is used if you don't specify the model you want to use. And in that case, that's perfect, because SST2, that's a model that has been fine-tuned on a sentiment data set. So that's a sentiment classifier that we now loaded. And you can see it downloaded some data. It's like about 300 megabytes that have been downloaded from the hub. So it went to the hub. You can also see here the link. If you want to have a closer look at what that model actually is, you can go to that link, and then it downloads it. If you execute it a second time, it won't download it again, because now it's already cached. So it knows we've already downloaded it, and it doesn't download it again. And then it's as easy as just passing the text through that pipeline object. So we can input it, so execute it to see that it's real. And you can see the predicted label is negative with a pretty high score, which is like, in that case, I think a percentage of certainty towards the label. If we wanted, we can also execute several at the same time. You can see we get a list of a dictionary. So if we add a second example, maybe I love transformers, and pass that through the model, you can see you get now two predictions. The first one negative for the text, and the second one positive because I love transformers. And that pipeline object is really great if you just want to try out like a new model and you want to see if that already works for your use case, or you just want to get like a quick baseline for what's possible with the transformer model. And also if you then later, after you go through the example with Lewis, once you trained your own model, the pipeline is really nice to just wrap all the pre-processing and post-processing in a single object, and you don't need to worry about that. Now, a second very prominent task that you can do with transformers is named entity recognition. So in our case, like we have a lot of named entities. In our example, we had Amazon in there, we had Optimus Prime, Megatron, Bumblebee. Those are all names, essentially, that are within the text. And named entity recognition tries to identify where these named entities are in the text. So it's a little bit different than text classification because we don't classify the whole text, but instead we classify each token of the text. So you can see here in the example we had before, like Krista Lanz loves San Diego. Instead of just predicting one class, now what the model does, it predicts one class per token. And you have two types of labels here. First of all, you have different types of entities. You have persons, for example, or locations, or miscellaneous is, I think, a third one that we're going to see. And then you have these prefixes like B or I, and they mean, B means that's the beginning of a named entity, and I means that's belonging to the last named entity as well. So you can see Krista Lanz is 3 tokens, and therefore you get 3 labels, and you can see that they belong together because the first one has a B and the other one have an I. At the same time, some words are not named entities. For example, loves. In that case, you get like an O for nothing. So we can play the same game again. Now we want to load a different pipeline. We now want to load an entity recognition pipeline. And when we do that, we get the same warning. We haven't supplied a model, so it loads BERT large case fine-tuned on the CONLL03 data set. That's a named entity data set on English. And you can see that model is a bit bigger than the last one. It's like 1 gigabyte, whereas the last one was just a few megabytes. So it takes like a couple of seconds more. But luckily, you only need to do that once. And if you're on Colab, you also have a pretty big bandwidth. So it doesn't take that long.
Hey, Leandro, we've got a question from M. Kumar. So they're asking, does the way the input text that's being fed into the model change based on the task or the model?
Not sure I understand the question. So the question is if the pre-processing is different based on the task. Is that
that's my understanding, yeah.
Okay. Yes, so depending on the task and especially depending on the model, the pre-processing can be slightly different. So one thing that is special to each model is it can have its own tokenizer. The tokenizer takes care of splitting an input text into these smaller pieces, and that's usually something that's built together with the model. So that's one different aspect, and sometimes there are also some other task-specific pre-processing steps. But at the top of my head, I can think more of like the post-processing steps that are definitely different for the different models.
Question answering, I think, is one example where you do post-processing to figure out where the answer is in the text.
Yeah. And actually, in a second, we're going to see like post-processing in named entity recognition as well. So we've now loaded the model, and you can see here we can add an aggregation strategy, which means if we have that case here where we have a named entity that consists of 3 tokens, we can just summarize that as one entity that has been detected instead of predicting 3 entities. And we can have a look at what that looks like. So now we have we get a list of a dictionary where we get different entity groups. So org means organization. We get a score that tells us how confident the model is that that's the actual correct entity. And we get which word was assigned to that entity. So Amazon in that case. Or we have a different one, which is maybe miscellaneous, and it's the word Optimus Prime. And Optimus Prime was very likely 2 tokens in the model, but because we set aggregation strategy to simple, it has been merged into one token. And we can just iterate through the entities that have been detected and format them a little bit nicer. And you can see it worked pretty well. I mean, it recognized Amazon as an organization. It wasn't quite sure what Optimus Prime is. It said it's like something miscellaneous. And then it got a little bit confused with the Megatron and Decepticons. So you can see for Mega, it assigned the class miscellaneous, where for Tron, it thought it's a person. And that's why also they haven't been merged together, because they're not the same type of entity. But that's also kind of expected, because that model that we used, that wasn't trained on these transformer characters. So it probably has never seen the word Megatron, so it doesn't know that that is a person or should be miscellaneous. And actually, would you say that a transformer is a person is a deeply philosophical question, maybe too deep for the model to answer. But in general, you can see that it works to some degree. So for that, we didn't have to do anything, and it was trained on a different data set. We can already like figure out some entities in the text. Now, another very exciting application of transformers besides entity recognition and classification is question answering. And in question answering, we're a bit more flexible in what we want the model to do. So we can provide the model with a text in question answering, and then we can ask a question about that text. And the task of the model is to find the answer to our question in the text we provided. Like technically, what the model does under the hood is for each token, it tries to determine whether that's likely the start of the answer or if that's the end of the answer. And you can see that here, like in the blue and the red bars. So the blue bars should show like the likelihood that the model thinks that's like the start of an answer, and in red, if it's the end of an answer. And then at the end, you just go and look for the most likely start and the most likely end, and you extract everything that's in between. This is also called extractive question answering, because the model only extracts the answer from the text you provide. Another form of question answering is abstractive question answering, where the model is more free and just can generate an answer by itself. So it doesn't need to be exactly present in the context that you provide. But for now, we just want to do extractive question answering. And to no surprise, we can do that again with like the pipeline, and we just load a pre-trained model. In this case, it's a distilled bird trained on Squat. Squat is a very famous question answering data set from Stanford, I think. And now we can ask the question, what does the customer want? And as a context, we provide the same customer feedback that we used previously. And we can see the model thinks the answer is an exchange of Megatron, which is correct. We want in the text, like what we ask for is that the model is replaced. Now we switch gears a little bit. So far, we've looked at like natural language understanding task, which means you take the input text and you make like a single predictions. Now we dive a little bit into generation. So generation is a little bit different, because you not only create like one prediction, but you generate some text, and generating text usually involves predicting the next word several times after the other. And here's like an illustration of that. When we want to generate some text, for example, transformers are, then we predict the next word. And then in the second step, we use the predicted word as an input and predict the word following that one. That's why usually these models are a little bit slower, because instead of just one pass through the model, we need to pass several times the inputs through the model. And one very cool application that you can do with generation is summarization. So you take a long text and you tell the model to generate like a short text from that. And let's download a summarization pipeline. Takes a couple of seconds. That's a BART model. That's a sequence-to-sequence model like T5 that we saw that has both an encoder and decoder, and it has been trained on CNN, which is a news data set where the task is to summarize long news articles. And what we want to do now is we want to pass the long text that we have, and we want to create like a brief summary. And that can be useful for all sorts of tasks. Like if you have many long documents in your company and nobody has time to read them, maybe you want to automatically generate like a short abstract for each document, like a preview. So if you're looking for something, you don't need to read the whole long document, but you can look at like a shortened version of it to get the gist. And we can, again, run the text that we had through the pipeline. We can specify how long the text should be maximally. And we also want to clean up some tokenization artifacts that we get. And when we then print the output, we can see that actually looks pretty good. I mean, Bumblebee ordered an Optimus Prime action figure from your online store in Germany. Unfortunately, when I opened the package, I discovered to my horror that it was the wrong one. I mean, that seems to be approximately right. What's maybe a bit weird is that it changes like the subject from third person to first person, but other than that, that's a pretty good start.
So, Leandro, before we go to translation, we have a question from Sylvester, who's asking if there are any tricks that one can use to improve the speed of doing inference, or just, embedding 100,000 plus sentences. They say the classical lookup with like word to vec is pretty fast, and can we do something similar with transformers?
So with transformers, there's several things that you can do. One thing that's pretty easy to do, and that's only require a few lines of code, is quantization, where you change the precision in a sense of the operations that happen within the transformer. And just by doing that, depending on your architecture, you can already get a speed up of a few times. So maybe the model is like 2 to 3 times faster after you do quantization. Another thing that you can do is there's a thing called the OwnNX runtime, which optimizes like the models further and also looks at the hardware that you actually use it on to make inference. So as I mentioned before, there's also that product that we recently launched called Infinity, and that takes it even a step further, where the model is optimized to a degree where creating one prediction takes like on the order of a millisecond, which is also pretty good for most applications.
That's great. We have a related question to summarization, which is from Amrit, and they're asking, is there any other better metric to gauge the coherence of a summary? The Roge score doesn't seem to do a great job, and do you know of any other metrics?
I'm not really an expert on that domain. Depending on what you want to do and whether it's more important to have all the information in the text or just a coherent sentences. For some applications, the Blur score is better, or there's also Meteor. And I think as a final thing, it's always good to have like just a human evaluation where you maybe prompt the model with 100 examples and then have humans label it to see what the acceptance rate is, because that's usually also what you care about in the end, right? It's like, what does the end user like it? And no automatic metric at the moment can capture that fully, I think. Maybe Lewis, you have something else to add, but that's my...
No, I think in general, like it's an open question of how do you kind of relate what a human would judge as a good summary versus the like the loss or the function that we choose to optimize in training. And to the best of my knowledge, I think OpenAI, their approach is like the sort of maybe closest we get to that, because they use reinforcement learning plus human preferences to figure out what is a good summary. But I think in general, like just having a single number capture the meaning of summarization is an open problem.
Yeah, I think what you mentioned is right. Like usually when you train the model, you optimize for loss, but the loss is not the same as, it doesn't optimize the same thing as the root score. So even if you have a lower loss, you might not have the optimal root score. And then there's an extra step where even if you have a good root score, it's actually not the thing you're looking for, because what you're looking for is the human acceptance. So I have like 2 steps between training the model and actually knowing that it's a good model, which is a challenging thing. And what you said is right, that OpenAI tries to shortcut that by training the model directly on human feedback and therefore optimizing for human feedback instead of like cross entropy loss.
And one last question about summarization. In the example that you showed, is it a case of extractive or abstractive?
In that summarization case, it's abstractive. So the model, as far as I know, is a sequence-to-sequence model, in which case it gets like the whole input as a sequence and then generates a new sequence. So it's generated, and I think, yeah, you can see that in the first sentence, right? That's not present actually in the input text that we used.
There's a related question, which is that, is question answering technically also a generational task?
It can be. So there, as I said, there are multiple flavors of question answering. There's extractive question answering, where it's more a classification task, and you try to classify the token that where the answer starts, and you classify the end of the answer in the text. But there's also abstractive question answering, where the model can generate an answer, and in that case, it's a generative task.
Yeah, and there's just one question from Nina. I can probably answer this one. So Nina's asking, it's probably asking too much, but is there an evaluation functionality that we can use on Hugging Face? So at the moment, we don't have something that just automatically evaluates a model for you through the hub. But what we do have at the moment is that every time you train a model using the trainer, which we'll see in the next section, it will automatically compute the evaluation metrics and show them to you on the hub. And we'll see an example of that later on. But that's a great question. And it's something we kind of have pieces of it in the infrastructure, but we haven't yet figured out how do you evaluate every possible model combination with every possible data set and task. But yeah, great question.
Yeah, and another piece of that is in the datasets library that you're going to show, there's also a metric function, so load metric function, where we provide like reference implementations of all the popular metrics. So if you want to calculate the root score of your dataset, of your model on some dataset, you can use that function without having to implement it and worry about the details too much. Good. I think I'm running out of time, so I'm gonna continue unless there are any urgent questions. So the last thing I want to show is translation. Translation is pretty important for many people, because very often, like maybe the text you get is not in the language that you actually understand, and a lot of people or companies relate heavily on things like Google Translate to help in these cases. But sometimes it would be nice to have an automatic way of do that, like on your laptop, maybe on many data points, and then Google Translate is not ideal. Another issue with Google Translate is that you, depending on the company you work for, you're not supposed to send sensitive information to Google Translate. So you can't translate everything with it. And fortunately, there are like a lot of models now in the hub that can do translation for you. And like one family of models comes from the Helsinki NLP team, which has provided, like, I think at the moment, about 1,000 checkpoints of models that can translate from one language to another. So 1,000 language pairs in a sense. Here you can see one language pair. It's a model that translates from English to German, but there are like 999 other language pairs that you can use. And let's see if we can translate that input text that we have to German and what that would look like. I mean, another cool application while that's loading of translation is data augmentation with translation. What you can do is you can take two models, one that translates to German and one that translates back to English, and you can apply that to your data set. And in that translation process, if you translate from English to German and back to English, there's going to be small variances in the text, and that can help you train models more robustly because you added some little noise to the text. So let's see what the translation looks like. Again, translation is also a little bit slower because you need to do that iterative generative process. And you can see like it looks pretty okay. Sometimes, let's see. I mean, it's not the best German I've ever read, but I mean, it transmits the meaning or translates the meaning okay-ish. So that can be a cool tool that you can use if you have a model that's in a language that's different to your data set. You can try to translate the data and then apply it to the model. Maybe if you have a classifier in English and your text are in Japanese, you can do something like that, or you can use back translation for data augmentation. Now, the last thing I want to show you is now I just loaded some default models most of the time, but maybe you want to use like a specific model for your use case. So you can go to the model hub. You just go to huggingface.co and go on models, and then you can see all the models that are available on the hub at the moment. And actually, I was wrong. It's more like 26,000 now, 26,000 models that you can use, that you can easily download and use for your use case. And some of these models, they have been trained for specific classes. For example, we looked at question answering, and we can just filter for models that have been trained on question answering. So you can see there's a wide range of models. I want to do something slightly different now. I want to do zero-shot classification. So I select zero-shot classification. And I want to do something multilingual. Usually, if you want to do something that's not just English, XLM Roberta is like a really good model to look for because that was trained on 100 languages. So usually it works pretty well on French or German or other languages. So we can have a look, for example, at that one here, like XLM Roberta. You can see there's some documentation to the model, and there's also a small widget, which is essentially an online version of the pipeline. So you can input some text, and you can, in that case, you can input some classes you want the model to classify. A zero-shot classification model is cool because you can specify any classes that you want, and it will tell you whether the text that you inputted is compatible with those classes. So that's different to normal classification where you have a limited number of labels and you just predict on those, where you can actually dynamically change the labels and see if it still works. And we can run it here. You can see there's some text that I can understand and some language that I can understand. I mean, at least I can understand the labels, but I mean, just for trying it out, you could also do something different and say, I really like transformers, and I can say my labels are positive and negative. I can see if that works. You see, it predicts the class positive with pretty high confidence. So that's cool. That's what I want to use, and you can see for many models, there's a lot of documentation of how you use them here. So we're gonna just copy paste that, and we can go back to the notebook, and you can see actually I already did it here. You just specify the pipeline, the zero-shot pipeline, and you can specify any model from the hub. So you just can copy paste that model name here, and you can input it to the pipeline. You should make sure that the model that you use is actually compatible with the task you want to do. And that's what I did by selecting the zero-shot task at the beginning. You can do the same for question answering or so. Otherwise, it might not work. So let's do that. And I did it here for an example that I thought you can see. I didn't just cherry pick that before, where I say the NLP meetup this week is only virtual, and then I use that zero-shot classifier, and you can see from the classes I provided, like meeting, work, digital, and travel, it selected digital and meeting as the most likely ones. Yeah, so that's zero-shot classification. That's just like scratching the surface. There are many more pipelines that you can use. There is also a text generation pipeline that you can use, or a conversational pipeline. And one thing that's been pretty exciting recently is that we branched out to different modalities. So we also host, for example, computer vision models. I linked here like a model on the hub for object detection, where you can see you input that image and it detects objects in that image. We've also been pretty active with audio models, especially like speech to text. Here's a model called Wave2Vec2, where you can either record some speaking from the browser, or you can upload a file, or you can use like a default thing on the hub, and you can see the transcript of the audio. You can just click here if you want to check it out. Yeah, here you can test it by, for example, recording some examples. And lastly, something that's pretty cool is table question answering, where your input isn't the text but a table, and you can ask questions about a table. For example, which is the repository with the most stars? And you can see the model then looks in a table. And that's it. Just a final note for the people who are running that notebook locally. Whenever you download a model, it adds it to your cache. And if you run that whole notebook end to end on your laptop, probably you now like acquire 10, 20 gigabytes of transformer models somewhere on your laptop, which might be not so good. And I added a note here where you can find that cache. And if you need to, you can delete it afterwards, so you don't fill up your laptop with transformer models, although that would make me happy.